Okay, the next speaker is Andrea Del Prete. Andrea is an assistant professor in the University of Toronto from 2019. Before that, he was in Max Planck Institute in Movement Generation and Control Group as a research scientist. He did a postdoc for 4 years in Geppetto team at last CNRS with Nicola Mansa. And before that, he did 3 years of PhD plus 1 year of postdoc at IIT Genova. So Andrea has done a lot of work on locomotion and a lot of very useful software for robotics like task space inverse dynamics. And we are looking forward to your talk. Andrea, please.
Thanks, Majid. Thanks for inviting me. So today I'm going to talk about task space inverse dynamics, which is a name that refers both to a mathematical framework that is used for doing robot control, and it's also the name of a C++ library that implements this framework. So I'm going to dedicate the first half of the talk to introducing the mathematical framework, so the theory, and then the second half of the talk will be dedicated instead to the implementation and the C++ library. So first of all, what is task space inverse dynamics, or TSID for short? Well, it's a popular control framework, especially used for legged robots and robot manipulators. It was a very active research area from about 2000 to 2015. Then after that, more or less everybody converged to a consensus, and so research on that subject kind of stopped, or at least slowed down. And you can think of this control framework as something that is similar to trajectory optimization, if you're familiar with that, but where the horizon over which you're optimizing is collapsed to 0. So it's trajectory optimization without a horizon. So it's instantaneous trajectory optimization. What are the applications for TSID? Well, TSID is quite flexible. It can be used for in different situations. Like for instance, if you have a reference state trajectory that you computed using indeed trajectory optimization, you want to track this trajectory on your system, you can use TSID for doing stabilization. Or maybe you don't have a trajectory for the complete state of your system, you just know the center of mass trajectory, for instance, and the fit trajectory that you maybe computed using a simplified model. Even in that case, you can use TSID for doing trajectory tracking. Or if you want to track a simple geometrical shape, like you want to follow a circular trajectory with the end effector of your robot manipulator, then again, you can use TSID. Or if you want to do balancing, TSID has been used quite a lot for doing balancing of legged robots. So I have a couple of videos to show you, just to give you an idea of what possible applications of TSID could be like. So here you can see on the left, TSID was used as a controller in simulation, and it was compared to an inverse kinematics position controller. And they also compared two different applications of TSID with position control and with torque control. And in this case, it was used on a humanoid for doing walking. On the right, instead, TSID was used together with a simplified model MPC for generating the trajectory of the complete robot. So for going from the simplified model, which only gave a reference for the center of mass, to the complete trajectory for all the joints of the system. And in this case, it was applied to a quadruped. So going back to the presentation, can you see my slides?
Yes.
Okay. So I will continue from my iPad so I can draw these beautiful red lines. So as I said, I will spend the first half of the presentation discussing the theory of TSID, and then the very last part is going to be about the implementation. So let's go a bit into the details of what TSID is about. In case you don't know anything about inverse dynamics, let's start from the dynamics of our robot manipulator. So mass matrix times joint accelerations plus nonlinear effects, which include gravity, Coriolis, centrifugal forces, typically also friction could be inside that, equal to the joint torques, which are generated by the motors. So the problem we want to face first is to find the joint torques so that the robot configuration, so the joint angles Q, follow a reference trajectory QR, which might be time varying. And what we assume is that we know the dynamics, so we know how to compute M and H, for instance, using Pinocchio, and we can measure the state of the system, so Q and V. So the solution to this problem is actually pretty simple and is given by the so-called inverse dynamics approach. So we set the joint torques tau equal to M times V dot desired plus H. So if we do so, since M is always invertible, it's very easy to see that if we plug that here and we simplify, what we get is that in the end, V dot is equal to V dot desired. So now we need to choose V dot desired, which is very simple because we have a linear dynamical system. And so we can simply set V dot desired equal to V dot reference plus a proportional derivative feedback term, which compensate for errors that we might have in the tracking of our reference trajectory. So we just need to choose then a proportional and a derivative positive definite gain matrices. And as long as these matrices are positive definite, we can be sure that the system is stable. So it's gonna be attracted by this reference trajectory. So this is the resulting control law, putting it all together, which is known in the literature as inverse dynamics control, but in robotics it's also called sometimes computed torque control. And this is a special instance of the so-called feedback linearization method from control theory because we are linearizing the system as I just showed you in the previous slide. So this is all very old style control approaches because this comes from the 50s, I think. But what has regained attention in more recent years is that you can cast this control problem as an optimization problem. The optimization problem looks like this. We want to minimize these two variables with respect to these two variables, tau and v dot, which are the joint torques and accelerations. Trying to minimize this cost function here, where you minimize the difference between v dot and v dot desired, where v dot desired is computed as before, subject to the dynamics of the system as constraints. And it's quite easy to see that the solution to this minimization problem is exactly the same inverse dynamics control law that we just saw in the previous slide. So you simply compute the optimal torques as m times the desired accelerations plus h. Very simple and actually not very interesting, because why on earth would we need to solve this optimization problem if you already know that the solution is this one? Well, there is no reason to do so, but this is going to be our starting point in order to solve more complex problems that take into account more constraints of our system. And the good news is that this optimization problem is a quadratic program. It's a convex QP, which can be solved extremely fast at 1 kilohertz, for instance, with using off-the-shelf open source software. So it's something that you can actually do inside a very fast feedback control loop. So one of the things that we can do to make this problem more interesting is that, for instance, we can add torque limits. So we can explicitly model in our framework that the torques of our robots are bounded. So we cannot apply infinite torque. And then the controller is going to take that into account. Similarly, if you're using electric motors, for electric motors, the torque and the current are proportional to each other. And so we can very easily introduce also bounds on the motor current. With a tiny effort, we can also introduce bounds on the joint velocities. We just need to assume that the acceleration is going to remain constant during the time step, which is a very reasonable assumption because the time step is so small that typically accelerations are indeed constant. So if we do so, we can represent the next velocity at the next time step as the current velocity plus dt plus times the acceleration. And by doing so, we can introduce also joint velocity limits, which are also linear constraints. So the problem is always a quadratic problem, even after we added all these constraints. We could also apply the same trick for introducing joint position limits. So expressing the joint position limits on the next joint positions, which are computed by simply integrating the desired accelerations. But this approach actually doesn't work very well because it typically results in very high accelerations, which might be incompatible with the torque and current limits. And so in the end, you can end up with a QP that is unfeasible. So in this case, if you want to do things properly, there are better approaches. For instance, you can take a look at this paper, which I wrote a few years ago, that explains how to do this in a more precise way that doesn't lead to infeasibility problems. But long story short, there are some simple approaches to introduce also joint position limits inside the TSID control problem. So we just went from the standard old school inverse dynamics control approach, where you don't have any inequality constraint, to this more advanced approach, where you solve a QP at each iteration of your control loop, and you can bound the torques, the current, the joint velocities, and the joint positions. So your control framework is immediately much more advanced. Let's take one step further, and let's assume that now we don't have a reference trajectory in joint space, but maybe we have a reference trajectory for the end effector of the robot, or for the center of mass of the robot, or maybe for the orientation of the camera of the robot. Actually, anything that is a function of the robot state could go in this list. So if you have a reference trajectory for one of these quantities, can we still use TSID? Yes, of course we can. And actually, the change that we need to apply to the formulation is very small. We are always solving a minimization problem, which is a QP, over the same optimization variables, which are the joint torques and the joint accelerations, subject to the same constraints, which are basically the dynamics of the system. The only thing that we need to change is the cost function. Before, the cost function here was something like norm of Q double dot, or actually B dot minus B dot desired square. And now instead we are doing X double dot minus X double dot desired, where we have expressed X double dot as an affine function of the joint accelerations, which is very simple to do, just computing the Jacobian of the quantities that we want to control. So this is going to be either the Jacobian of the end effector, or the Jacobian of the center of mass, or the Jacobian of the orientation of a frame. And all of these quantities can be computed, again, using the Pinocchio library that Justin just presented before me. So a very small change, and again, we maintain the structure of the problem, which is a QP. Can we do more? Sure, we can. So let's talk a bit about underactuation. So far, we have dealt with the dynamics of a robot manipulator, which is a typically fully actuated system. So you have one motor for each joint, and the problem takes this form here. Where now I wrote down the dynamics in matrix form, but it's just the same equation we saw in the previous slide. The problem is that many interesting robotic systems are not fully actuated, they are underactuated. So the number of actuators is less than the number of degrees of freedom of the system. So that's the case for all mobile robots, basically. So legged robots, wheeled robots, flying robots, underwater robots, they're all underactuated typically. So how can you extend TSID to handle underactuation? Again, it's a very small change in the framework. So instead of having here the identity matrix, we introduce this selection matrix S, which, for instance, for a legged robot would look like this. You would have 6 columns of zeros here in the first 6 columns, and then you would have simply the identity matrix. So this matrix is basically selecting the degrees of freedom of the robot which are actuated. And just by doing this very small change in your mathematical formulation, now you can handle a system that is underactuated. And this was not possible in the original inverse dynamics control law. Another feature that is very often useful and that Justin just actually discussed in great length is rigid contact constraints. So especially if you're working with a legged robot, so a biped or a quadruped robot, the robot is almost all the time in contact with the environment. And very often these contacts are modeled as rigid because that's very convenient in practice. So when you have a rigid contact, you basically are introducing a constraint because the robot can no longer move in the direction of the contact because otherwise it would penetrate the environment, which is not possible. So what you can do is that you can model that constraint using a mathematical equality, which is basically saying that the contact points do not move. Then to introduce this inside the TSID optimization problem, we need to take the derivatives of this constraint because Q is not part of the decision variables of our problem. So you differentiate the constraint twice and you express it at the level of acceleration, which is basically the same as saying that the contact point accelerations are null. After you've done that, you can introduce this equation here as an additional equality constraint in your problem. But you need to do something more. In this case, you need to also extend the number of decision variables of your problem to account for the contact forces, which are going to appear in the dynamics through the use of the Jacobian transpose, which multiplies the contact forces in the dynamics of a robot that is in contact with the ground or with any actually part of the environment. So in this case, the problem has changed a bit more, but again, it maintains the structure of a convex quadratic program. So it's still an optimization problem that can be solved extremely fast using the same kind of solvers that we were using before. So it's not a drastic change. So once again, the main benefit, at least as far as I'm concerned, of using optimization is that you can introduce inequality constraints. So if we want to maintain the problem a quadratic program, then we know that we can introduce any linear inequality constraint. So any inequality constraint that is a linear function of the joint torques, the contact forces, or the joint accelerations. So for instance, now that we have contact forces, we can introduce friction cone constraints by linearizing them. So approximating the quadratic friction cone with some pyramidal function, doing something like that. And you can make it as precise as you want by introducing more shapes, so more boundaries for the pyramidal approximation. You can also introduce collision avoidance constraints, which are a bit more complicated. And of course, you can always use the simple constraints, such as the torque bounds or the joint velocity bounds that we described before. Another very important aspect is that very often, if you're controlling a complex robot, typically the robot is going to be redundant with respect to the main task that you want it to perform. So for instance, if you are controlling a 7 degrees of freedom manipulator, and you want to control the placement of the end effector, which is 6 degrees of freedom as a task, you have 1 degree of freedom of redundancy because 7 minus 6 is 1. If you have an 80 degrees of freedom biped, and you want to control the placement of the 2 feet. That's a 12 degrees of freedom task. So you're going to have 18 minus 12, so 6 degrees of freedom of redundancy. So clearly, you would like to exploit this redundancy in order to optimize the motion, or maybe to achieve some secondary tasks that are not as important as the main one, but still you would like to achieve them at their best. So in this case, which is very common in practice, you want to express a cost function for each of the tasks that you want to achieve. So we're going to end up with a list of cost functions, let's say from 1 to n. Each cost function is going to be a convex quadratic function like this one. And a very simple strategy to account for all these tasks at the same time is to sum up the cost function altogether, but using different user-defined weights, WI. So each task is going to have a different weight, which is a positive scalar that the user must define. And clearly, the higher the weight is, the more important the task is. And so the higher the probability that the task is going to be achieved with a great accuracy. So typically, we're going to assign very high weight to the tasks that are very important and very low weight to the tasks that are instead secondary. So the pros of this approach is that the problem remains a computationally efficient QP. So you just solve a single convex QP as you did before. The problem is that if you have many such tasks to achieve, then tuning the weights might be a bit tricky, because if you have weights that are too large and small with respect to each other, this might lead to numerical issues. So your QP solver might have a hard time finding a solution, or it might even fail. That is why there is another approach, which is a hierarchical multi-objective optimization approach. In this approach, instead of assigning a weight to each task, you assign a priority. So you're saying that task 1 is more important than task 2, task 2 is going to be more important than task 3, and so on and so forth. So after you have defined this priority list, you can solve a sequence, also called cascade, of optimization problems from 1 to capital N, where in each problem you're minimizing just one task function subject to the usual dynamics constraints, but you're also adding an extra constraint that says that the cost function associated to the task with a higher priority must remain at the optimal value that was computed in the previous optimization problems. So in this case, you're going to end up solving not one optimization problem, but n optimization problems. So it's going to be more computationally expensive, but the advantage is that it's going to be easier for you to find priorities than to finding weights, because you need to basically assign only an integer value to each task instead of a scalar real value. So you have many more options, so many more probabilities of doing it wrongly. So that's it for the theory of TSID. I don't know if there are any questions so far. Maybe Majid can.
I don't see anything, so I think
okay.
we can go ahead for now.
Okay, thanks, Majid.
Yeah.
So let's now talk about the implementation of this theoretical framework in an efficient C++ library. So TSID is an open source library implemented in C++ with Python bindings, and you can find it on GitHub at this address. TSID relies on a few very efficient C++ library for its computation. So we use Eigen for doing linear algebra computations. We use Pinocchio, which was just presented by Justin, for anything that is multi-body dynamics. And we use AQuadProg for solving convex quadratic problems. So pros and cons of TSID. Well, it has some missing features. So with respect to everything that I've just discussed on the theoretical side, some features are not implemented in TSID. Probably the main missing feature is that we don't have the hierarchical approach implemented. We only have the weighted approach for doing multitask optimization. We don't have bilateral contacts yet, and we don't have line contacts, and probably there are many other missing features that are not implemented yet. But then we have also a very long list of advantages of TSID. It's very efficient, so you can solve the TSID control problem in less than 0.6 millisecond for a humanoid. It has been tested on humanoids and quadrupeds. It's an open source software. The design is actually quite modular, so it's very easy to extend, and we do extend it upon demand. It comes with Python bindings, so it's very easy to use it just from Python. It's very easy to install because it comes with Debian packages, so you can install it just doing sudo apt install name of the library. It comes also with a lot of educational material because I use it quite a lot in my classes on robotics, and I've taught classes about TSID in winter schools and summer schools, so the material is available online. And also another advantage is that there are not many alternatives available. As far as I know, the only one that I know of is this Orca framework, but it has different pros and cons with respect to TSID. So TSID also comes with a quite active community that is supporting it. I'm going to give you some numbers. So in the 4 years that has passed since it was created, we have had more than 400 commits, more than 50 issues closed, more than 60 pull requests, and 35 forks of the library. So just in the last 2 weeks, TSID has been cloned 18 times, and the page has been visited 47 times, which is more than I expected. We have also quite a long list of contributors, and probably the main developer, and Justin is the second on the list. And I should also mention Guillaume, which provides a lot of technical support, both for TSID and actually also for Pinocchio. And then we have also a list of more sparse contributors which are just contributing from time to time for very specific features from very different universities and research centers. So let's go into the core of TSID, and let me describe how TSID has been designed. So the key concept inside TSID is the concept of task, which is something that you would like the robot to do for you. And a task can be a motion task if it is expressed as a function of the accelerations, a force task if it is expressed as a function of the contact forces, or an actuation task if you express it as a function of the joint torques of the robot. Another key concept of the library is the concept of rigid contact, which is quite similar to a task, but on top of that, it introduces reaction forces into the optimization problem that you want to solve. So it's different from a task, so we need to model it with a different objects. And then you can create all the tasks that you would like your robot to perform. You can create the rigid contact associated to the contact interaction between the robot and the environment in case your robot is in contact with the environment. And you can put them all together inside this other object here, which is called inverse dynamics formulation, which is basically just a collector of tasks and rigid contacts, and that contains all the code for translating task and rigid contacts into a hierarchical quadratic program. So why a hierarchical quadratic program? Well, as I said, at the moment, TSID doesn't implement the hierarchical approach, but the API has been designed to support hierarchies. So in the library, you will see that we always represent quadratic programs as if they were hierarchical, even if we don't support at the moment the solution of hierarchical QPs. Then once you have translated the problem into a HQP, you have a class which is a HQP solver that is just a solver for finding the solution. So just very briefly, a few of the methods of the inverse dynamics formulation class. You have a method for adding motion task, a method for adding force task, and another for adding actuation task. When you add a task to the problem, you can specify the weight and the priority. So the priority is an integer and the weight is a double, so a floating point value. You have another method for adding rigid contacts. And then finally, you have a method for computing the problem data. So for translating the robotic control problem into an optimization QP problem. This is a list of some of the tasks that are implemented inside TSID. You have a task for controlling the joint posture, so the joint angles, a task for controlling the position and orientation of any frame of the robot. So for instance, the end effector frame, if you want to control position and orientation of the hand or the foot of the robot. You have a specific task for the center of mass of the robot, another for the angular momentum, and another for the center of pressure in case your robot is walking on a flat ground. Then you have bound tasks, which are translated into inequality constraints. You have a task for the joint bound, so this is used for representing joint position, velocity, and acceleration limits. Another one for the actuation bound, so again, joint torque limits. And then you have an inequality task for representing the capture point inequalities. This is very useful if you want to do balancing on a legged robot. Yet another very useful feature is the mask. So every time you create a task with TSID, you can specify a mask, like we did here for an ST3 task, which is basically selecting which directions of the task you actually want to be active and which one you want to be inactive. So in this case, we are selecting the first 3 directions as active and the last 3 as inactive. And the first 3 correspond to the translation, so the position, whereas the last 3 correspond to the orientation. So basically, we are using a ST3 task, which would by default control both position and orientation to control actually only position. We could have done also the other way around and controlled only the orientation and not the position, or we could have also controlled a subset of position and orientation. Any subset would have been fine. And mask can be applied either in the local frame or in the word frame. So typically the word frame is going to be more common. Regarding the contact models, at the moment, TSID supports 2 contact models. One, when you have a contact between surfaces, such as the one between the foot of a humanoid robot and the ground. This is called contact 6D because it constrains the motion of the foot in all 6 directions, so 3D position and orientation. Because once the foot is in contact, it cannot move nor rotate. Then instead we have the contact point model, which is used when you have a point-like contact. This is typically used for quadruped robots because the feet of this robot is very small, and so it allows them to still rotate after making contact. So in this case, the only quantity that is constrained is the foot position, but not its orientation. Every time you introduce a contact in the formulation, automatically TSID also introduces friction cone constraints to represent the boundaries that you have on your contact forces. The friction cones are of course linearized by using as many edges for the pyramid as you specify. Each contact also introduces automatically a force regularization task, which is very useful for regularizing the contact forces and making sure that the solution that you get to your problem is not jumping from one iteration to the next one, which might happen if you don't regularize contact forces. And can also be used to, for instance, introduce robustness into the problem by keeping the contact forces close to the center the friction cone. So a few words on the QP solvers. So at the moment, you have several different solvers implemented inside the software. None of them supports a hierarchy, as I was saying before. So inside the HQP problems, basically, you can have only two hierarchy levels. One corresponds to the cost function, and the other one corresponds to the constraints. So all the solvers are based on A-quad-prog, which is a modified version of the solver U-quad-prog++ working with eigen. To improve efficiency, we actually optimize this solver, creating two new versions. One is called A-quad-prog real-time, which is the fastest, but it only works when the matrix sizes are known at compile time, which might not be always the case. If that's not the case, you can use the other version, which is called A-quad-prog fast, which allows for dynamics matrix sizes and performs only memory allocation when you're resizing the problem. Otherwise, there is no memory allocation going on at solution time. So these are a very old benchmarks that I did when I was still working at LAS. So in 2017, I did this benchmark on the computer of the HRP2 robot, which is a very old computer. So this is a sort of worst case benchmark. You can see that on average, I was able to solve the TSID problem for a humanoid in less than 0.6 milliseconds, even with a very high number of active inequality constraints. So I expect that by now, if you do the same on a modern computer, you should be able to be below half a millisecond of resolution time. Okay, that concludes my presentation on the implementation of TSID. So to summarize, why should you be interested in using TSID? Well, TSID is a very common control framework for legged robots and robot manipulators, but not limited to these two kind of robots, actually. It comes with an open source C++ library, coming with also Python bindings, which are very, very practical for bootstrapping the learning of the library. It can be very easily installed using Debian packages, so you can just do sudo apt install to have it running on your system. There is an active community behind it that is supporting the library, and it is being designed in a very modular way, so it can be easily extended. So even if some features are not implemented, it's quite easy to add them. And there is also quite a lot of educational material online, such as slides, videos, and examples, or for instance, this presentation, which will be made available online, I guess, that you can use in order to learn how to use the software. So I would stop here, and I would be happy to take any questions if there are any.
Okay, thanks a lot, Andrea, for this beautiful presentation. I think it was very tutorial-like, and it would be very useful for people. So yeah, please send questions on the chat if you have any. So actually, one question came to my mind when I was listening to you, Andrea. Does TSID support the bilateral contact, for instance, a hand grabbing the environment?
No, that was one of the missing features that I was mentioning. Mm-hmm. It's really trivial to support the bilateral contacts. Mm-hmm. We should just remove the friction cone constraints, basically. Mm-hmm.
But there might be some bilateral contacts that have friction cone. For instance, a hand grabbing a pipe. Then you have one directional friction constraint. So I think it's not a very trivial problem. There can be, depending on the degrees of freedom of motion, you can have different types of bilateral contacts.
Yeah. You can imagine very complex contact geometries that result in weird friction constraints, as you just described. Those are not implemented in TSID, but as I said, the design of the library is quite modular, so it should be easily possible to add them. For instance, the contact point model was added years after I developed the first version of TSID. by Julian, and he was able to add it without changing the API. So I hope that even these more weird models should be feasible.
Okay, great. So I think we are exactly on time, and so we can end this part here now. Thanks a lot again, Andrea.
Thanks to you.
So